We'll now look at methods for improving longitudinal stability control. Information for this topic comes out of Chapter 27. Again, for longitudinal stability, we look at the CG envelope and we know that the forward limit is set by controllability, and the aft limit is set by stability. So after the concept and design phase, a prototype aircraft eventually reaches flight test. So what can a test pilot or FTE do to improve longitudinal stability and control without having to redesign the wings, move the tail back, all these other costly things? Because those major redesigns would add to the schedule and to the cost. Plus, predicting or modeling the control hinge moments and control coefficients that's done in the design process is difficult even with the best information, so we know that aircraft are going to get to flight test and still have issues. There are several things we can do without a major design change, and we'll go from simple to more complex. So fixes that would require the least change to the airplane are the ones we would try first. We might call these gimmicks or stability augmentation systems, but in these systems, we do not really change the stability and control. We just kind of fool the pilot to thinking we have. It's worth noting that some of these systems work for both reversible and irreversible control systems. We'll start with stick centering spring. This centers the stick and adds force increment, which depends upon the stick displacement, along the lines of Hooke's law. It improves control force at low speeds for both static and maneuvering stability. The effect diminishes with increase in airspeed for a reversible control system because the control displacements also diminish. For reversible control systems, the stick does not trim to the same position for each trim speed, causing a force bias. Such a problem is not the case for an irreversible control system, as the controls are fixed by mechanisms. They also work well for rudders and ailerons on reversible systems, where the control always returns to the same center trim location. An example of a stick centering spring is shown in the picture below. The elevator down spring, like its name, makes the elevator float down. With the spring installed, additional trim tab deflection must be added to cause the elevator to assume its original position. This causes an additional stick force gradient at all airspeeds. Since the force increment is not a function of stick position or NZ, the downspring does not improve maneuvering stability. It also can cause the phugoid to become less stable. The downspring can only be used with a reversible control system. An example of a downspring is shown in the diagram at the bottom of the page. The bob weight is a mass on an arm placed in the control system to provide a constant force. And like the downsprings, bob weights cause the elevator to float down. When maneuvering, the force input of the control system is multiplied by the load factor NZ. In addition to improving maneuvering stability, the bob weight also helps damp out the phugoid motion. But there are a couple of disadvantages. The first is it may cause stick pumping feedback into the control system in rough or turbulent air. Another disadvantage is the actual weight added to the system by the bob weight. This diagram shows an alternate location for the bob weight that can be used to improve flight in turbulence. In order to reduce the weight penalty of a bob weight, we can join it to a spring. And by tailoring the size of the bob weight with the spring constant of the downspring, it's possible to adjust stability levels to a desired value. The combination of weight and spring can be designed to meet space limitation problems, as is shown below with the aluminum tube option. If the simple springs or weights are insufficient to fix the problem, then we can add an elevator tab, which is a slightly more complex option. Several varieties of tabs that can address several stability and control problems are shown below, and we'll walk through all 4 of these one by one. A balance tab is a geared tab that can be made to either lead or lag the elevator movement. The gearing ratio of the tab may be adjusted by the size of the control horn or the push rod. Leading balance tabs increase stick forces and stability levels. Lagging balance tabs reduce stick forces and also reduce stability levels. The leading balance tab is a very effective device for fixing longitudinal stability problems. It reduces the tendency of the elevator to float. It shifts the stick-free neutral point aft, which helps the dynamics. Stick-free maneuvering stability is also increased since tabs input to the control system is a function of the elevator deflection. In some aircraft, they can sacrifice a little bit of stability margin to gain more maneuverability, and so they do use lagging balance tabs. Here's an example in the F4 Corsair. The tab is geared to deflect proportionally to the control deflection, but in the opposite direction. And both elevator up and elevator down are shown, and you can see how the tab does indeed deflect in the opposite direction. The Servo Tab actually drives the control surface. In this manner, large control surfaces may be deflected with reasonable control forces. Servo tabs found much use on aircraft like the B-17 prior to the advent of hydraulically boosted controls. A spring tab is a variant of the Servo Tab with a spring installed to restore some of the force deleted by the Servo Tab. By tailoring the spring constant, the force level can be adjusted to desired levels. Spring tabs were used on some early jet aircraft such as the P-80 and the T-33 to avoid hydraulic systems in the longitudinal control circuit. However, a potential problem with spring tabs is flutter. The spring-loaded tab is spring-loaded in the up position so that it floats the elevator down like the downspring. It provides both the benefits and drawbacks of the downspring with one additional drawback, flutter. As a result of flutter tendency, the spring-loaded tabs do not find much use. We'll now switch to a different technique involving aerodynamic balance. So if none of our attempts so far have fixed our stability problems, we may want to consider additional aerodynamic changes. There are several varieties of aerodynamic balance that can address stability control problems, and again we'll walk through all 5 of these here one by one. The overhang balance is a control surface area ahead of the hinge line. That's why it's sometimes also called a setback hinge line balance. It tends to reduce the floating tendency of the elevator. This is caused by the chord-wise pressure distribution of the surface. However, since a change in the overhang balance is a difficult change, both from the standpoint of estimating the effects and the physical change itself, it is likely one of the last things we would try to fix stability and control problems. The horn balance concentrates the balance area ahead of the hinge line. It is usually located at the tip of the elevator. And there's 2 types of horn balance, shielded and unshielded. The causes and effects are the same as overhang balance, but is more often used as a flight test fix than the overhang balance because it's physically easier to do. The internal balance with flexible seal works in the same manner as other aerodynamic balances. The flexible gap seal may be easier to install during flight testing and has added benefit of reducing drag. Adding blunt trailing edges tend to increase control forces by providing a better restoring tendency of the elevator. It has also been used successfully as a fix for elevator short period problems. It's a fairly simple change to make during flight testing, but may be difficult to tailor. The beveled trailing edge may be used to reduce control forces. It's not as simple a change as blunting, but it's used, and the Mooney aircraft uses this method to reduce aileron forces. So in conclusion, all of these simple stability augmentation systems may be used separately or together and may save the cost and complexity of more modern systems. But the next time you go to an airport, look around the airplanes and see how many of these flight test fixes you can find.